So last time we talked about random variables, and for random variables we have discrete random variables, okay, which means the possible values are discrete. For example, here the random variables, the possible values for a certain experiment is 0, 1, 2, 3, and 4. And for each of these outcomes, we have px. Px is the probability that certain values occurs. Okay, and the px added together should always be 100%. Okay, so this is the discrete variables. So continuous variables is continuous if its property are given by the areas under a curve. Okay, there's no gap between the possible values in that case. So let's see. Here is a histogram of speed of cars. Okay, so for example, number of cars is 100. Okay, this is histogram of the frequency for the speed of the cars, which is discrete variables. Okay, so we can put the gap or width of each rectangular as 1 mile per hour. Okay, the frequency shows, for example, around 50 miles per hour. The frequency is around 15. So 15 cars has a speed of 50 per hour with that range. Okay. If we increase the size of the sample to 1,000, okay, and then the gap or the width of the rectangular becomes smaller. Okay, in this case, the gap is 0.1, 0.5 miles per hour. Okay, so we have more sample size. The intervals, on the other hand, become smaller and smaller when we increase the size of the sample. And here we have 10,000 cars. Okay, again, the interval become even smaller. And this one is we have 1,000 cars, 100,000 samples. Okay, so what we can notice is when we further increase the sample size n, okay, the histogram, the top of rectangular become smoother. Okay, so the histogram will become like a curve. Right. So until we further increase the sample size n, it will become a continuous random variables. Okay, so to calculate the probability, instead of adding all the probability for each rectangular, so we calculate the areas under the probability curve. Okay, so areas under that curve will be the probability. So that is continuous random variables. And there's a name for that curve. This is called probability density function. Okay, so the curve is called probability density function, or PDF, for the random variables. Okay, there's another name for PDF is probability distribution. Okay, remember for discrete variables, it is called probability mass function. Okay, or PMF, like we discussed Tuesday this week. Okay, for continuous variables, it has a different name, which is PDF, probability density function. Okay, and x is a continuous random variables, the density function fx, and then if we do the integration for all the possible value of fx, it will become equal to 100%, equal to 1. Okay, so which means, again, the total areas under that probability density curve is equal to 1. Okay, so that is similar to what we discussed for discrete variables. Okay, for discrete variables, all the possible value, the probability added together is also equal to 100%. Okay. For continuous variables, the areas under the fx curve is equal to 1. Okay. To calculate the probability, okay, if let's see a and b are two numbers, b is larger than a, then the probability of x between a and b will equal to p for x larger or equal to a and smaller than b. So which means for continuous variables, the endpoint does not really matter. You see from here, the probability for x larger or equal to a and smaller or equal to b does not change when the endpoints is included or not. Okay, so that's true for continuous variables. Again, for endpoints, here is we have two endpoints, a and b. Whether the endpoints included or not for the probability does not affect the probability. Okay. And to calculate the probability for x less or equal to a, we do the integration from negative infinity to a. Okay. Again, the endpoints does not matter. For probability for x larger or equal to a, we do the integration between a to positive infinity. Okay, let me share my iPad with you. Again, the important difference between continuous and discrete variables, one of them, the important point is the probability does not affected by the endpoints. To calculate the probability is very straightforward. So we do integration of fx. Okay, it's just pure math. Let's do an example together. Any questions before? Questions? Okay. So the waiting time until service at hospital emergency department is modeled with PDF of these two functions. Okay. So when x between 0 and 3, this is this. Between 3 to 6 hours, fx become this. Okay. So the question is asking a series of questions. For example, the probability the wait is less than 4 hours, or the wait is more than 5 hours, okay, or the wait is less or equal to 30 minutes, and so on. Okay. So first of all, let's get an idea of what the curve looks like. What's the shape of the curve? Okay. So based on the first equation, between 0 to 3, this is 0, this is 3, okay, it is over 1 over 9 times x, okay, so when it becomes 3, the y-axis will become 1/3. Okay, so this part is a straight line. Okay, and for between 3 to 6, it becomes the second equation. Okay, so when x equal to 6, fx will become 0. Okay, so the shape of the curve will be something like this. Okay. Okay, then let's look at the first part of the question. Probability the wait is less than 4 hours. Okay, so less than 4 hours. So 4 hours here. So we simply do the integration to calculate the areas here. Right. So which including two parts. One is for x between 0 to 3. The other is between 3 to 4. Right. So we just do the math. Part A, px less than 4, right, which is equal to fx dx between 0 to 4. Okay, so that including two parts. Okay, one is from 0 to 3. From 0 to 3, the fx is this. Okay, so 1/9x dx plus from 3 to 4. So from 3 to 4, fx will become 2/3 minus 1/9x dx. Right? So this will become pure math questions. We do the integration. Okay. Square. So 0 to 3. Right? Okay. And then the second part will become 2x minus 9 times 2 x squared for 3 to 4. Okay, and then remaining you know how to do that. Okay, so plug 3 into x minus plus 0 into x, and for this part is plus 4 into x minus plus 3 into x. Okay, so this is a math question. For B, probability wait is more than 5 hours. Okay, so more than 5 hours. Again, let's look at the curve. Let's see, 5 is here. So more than 5 hours, that's this area, right? So again, we do the integration for part B. P x larger than 5. We do the integration between 5 to 6. Right? Don't get the wrong fx. That fx will be this. Two over 3 minus 1/9x dx. Okay. Then that will become between 5 and 6. Okay, that's B. C is similar. Probability the wait is less than or equal to 30 minutes. So 30 minutes is half hour. Here, so that is this area. For px less or equal to half hour. Okay, again, the endpoints doesn't matter. So less than half hour, the probability is same as less or equal to half hour. Okay, because this is a continuous variables. So for that part, we do integration between 0 to 0.5 because less than 0 has nothing. Okay, so we only do 0 to half. Okay, so fx dx. Okay, so fx is the first part. This part length is 1/9x. Okay, dx. Okay. Okay, so that's part C. Part D is a little bit different. Okay, so wait time that is exceeded by only 10% of the patient. 10% of the patient. So that is asking what is the time t what is time t that only 10% of patient waited more time than that. So the areas under the curve between t and 6 will be 10% or 0.1. Okay, so part D will be 10%. Again, the areas under the curve is probability. Right now the probability is 10%. Okay, so 10% equal to px larger than t. Okay, and we try to find out what is t. Okay, so based on the shape of the curve, we know the t will occur somewhere between 3 hours and 6 hours. Okay, so because the shape of the curve tells us 10% is somewhere between 3 and 6, cannot be here between 0 to 3. Otherwise, that area is be too large to equal to 10%. Okay, so we know it will be between 3 to 6. So t integration between t to 6. In that part, fx will be 2/3 minus 1 x dx. Will be this part. Okay, second part. Then just do the math again. Okay, so that's part D. Just let me know if you have any questions in the meanwhile. Okay. Part E, the mean value. Okay. Before we do the part E, let's see the equation for the mean value for continuous random variables, which is shown here. Okay. The mean value for continuous random variables is mu x equal to integration x fx dx. Okay, x fx dx. So using that equation, let's go back to part E. Okay. Mu x will equal to integration x fx dx, right? And that will including two parts. from 0 to 3 and from 3 to 6. So from 0 to 3, fx will be 1 over 9x. Okay, so x times 1 over 9x, so this is fx dx. And plus the second part from 3 to 6, okay, and x fx from 3 to 6, fx will become this dx. Okay, and then you can just do the remaining part of the mass integration. Okay, so any questions for this example?
I'm still confused about D.
D.
Yeah, is that 100 over a 0 or is that 10%?
A part D.
Yeah, in D, in part D.
10% of the patient. 10%
Okay,
of the
10.
patient. Yeah, so which means here,
10%.
this part will be 10%. This is 10%.
Okay.
Okay, so 10% of patient weighted more than T. Okay, but we don't know what is T now. So based on 10%, we figure out what is time T is. That is part D. Okay. For part A and B, we know how to integrate, the range to integration. For example, from 5 to 6. But for this part, we know the probability, which is the areas and the curve is 10%. What we try to do is we try to find out what is T is.
And for E, mu is the notation for the mean?
Yeah, mu is the mean. Yeah, the mean value is we call it mu x. Mu x.
Could you scroll back up to to E, please? I'm still trying to figure that one out.
The mean waiting time.
And that's just from negative infinity to positive infinity?
Yeah, but for this case, from 0 to 6 only. Because there's nothing outside 0 to 6.
For part D, you just end up with a function of T, right? And then if we were given like
Yes.
population.
Yes. Yeah. Based on this, 10% is equal to this equation, right? And there's only one unknown for this equation, which is T. So resolve T for that.
Okay, thanks.
Yeah. Okay, thank you for the question. Let's continue. All right, cumulative distribution function. For discrete variables, we also have cumulative distribution function. Okay. For continuous variables, it will be this. Fx equal to integration between negative infinite to x ft dt. Okay. So that is the probability that x less than certain value. Okay. The equation for me is given here, as we just did. And the variance equation is given by here. Okay. So the variance sigma x squared is a function of mean mu x and fx. Okay. You can use either one of these two equations. So for the previous example, if the question is asking what is cumulative distribution function, okay. So cumulative function fx, we do the integration from negative infinity to x, fx dx. Okay, so that will be different based on where the x is. Okay, so if the x is less than 3, then fx will be from negative infinity to x, okay, 1 over 9x dx. Okay, because nothing less than 0, so it could become 0 to x, 1 over 9x dx. Okay, so for x less than 3. If the x is between 3 to 6, then fx will become two part. Okay, one is between 0 to 3. The other part is between 3 to x. Okay, so if the x is here, then the cumulative function will be the areas under this curve, right? So which become two part. One is this part from 0 to 3. The other part is between 3 to x. Okay. Okay. All right. For For the first part, it becomes this. For the second part, become 3 to x. Okay, and simplify that. And then we have last part for x larger than 6. If x is larger than 6, then what the fx will be. So if x is larger than 6, if the x is here, what is cumulative function will be? Anybody have an idea? Without calculation? So the cumulative function again defined as the probability or the areas under the curve less than certain value x. Okay, and we already yes equal to 1 because we know the areas under this curve or the shape of triangle is 100% of 1. Okay, so when x larger than 6, so all the possibility added together will equal to 1. So without calculation, we know it is equal to 1. Okay. Okay, so questions about this before we get to the next question.
Yeah, I'm sorry. Can you repeat that last part? If it's greater than 6, why is it equal to 1?
If it's greater than 6, we're gonna consider the fx, the cumulative function will be this area, this is the whole triangle, right? Because what is cumulative distribution function? Is defined as this. Okay, so the probability between negative infinity to x. Okay, so when x is equal to 6, is larger than 6, so that probability cumulative function will including all the probability under this curve. Okay, and we know that is equal to 100%. So that's always true. For probability density function, the areas under the curve always equal to 1 or 100%. So that's probability, right? So the highest possible probability is 100%. Okay. All right. Any other questions? Okay. The next question is again is similar to the first one. A lot of integration, but let's do it together. Okay. So a hole is drilled in a sheet metal component, and then a shaft is inserted through the hole. Okay. The shaft clearance is equal to the difference between the radius of the hole and the radius of the shaft. Okay. X is the clearance in millimeter, given the probability density function of Fx. Okay. All right. So first of all, let's try to plot the general shape of the curve. Okay. All right. So Fx is non-zero only between 0 to 1. Okay. So let's see what is Fx equal to when x equal to 1 to 0. So plug 0 here. So Fx become 1.25. Okay, and when x equal to 1, okay, then Fx becomes 0. So the shape of the curve is something like this. Okay. Right. Okay. And the areas under that curve is the probability. Okay. Part A, component with clearance larger than 0.8 millimeter must be scrapped. 0.8. What proportion of components are scrapped? Okay, it's asking the probability the clearance is larger than 0.8. So actually, the areas under this curve, the shaded area. Okay, so P x larger than 0.8. So what we do is we do the integration between 0.8 to infinite, but only to 1. Okay, because larger than 1, that's nothing. Okay, and Fx is 1.25 this. Okay, and dx. Okay.
I'm sorry, that says 1.25 t, or is that 1 minus x?
1.
I can't understand that.
1.25, 1 minus x. This is this one.
Oh,
Fx.
okay, 1 minus x
That is this.
to the 4th power.
Yeah, yes. Yes, to the first power. It's Fx. Okay, Fx. So because based on the cumulative function, it is equal to 0.8 infinite Fx dx. Okay, and Fx is this. Fs is this. Okay, yes. Okay. Then which is equal to 1.25 x. This is x to the power of 5 between 0.8 and 1. Okay. And if you do the calculation, is equal to about 8.19% larger than 0.8. Okay, so we calculate the areas, the pink area between 0.8 to 1. Next part is asking for the cumulative distribution function. Okay. So for the cumulative function, again, we should see like 3 parts. One part is for x value less than 0. Okay. That's easy, which is equal to 0. There's nothing less than 0. Then for the x between 0 to 1, okay, and also for x value larger than 1. Larger than 1 is also simple, which is equal to 100%. Okay, so again, the fx, we do the integration from negative infinity okay. So depending on where the x is, if x less than or equal to 0, okay, then fx is equal to 0. Right, so 0 dt is equal to 0 because nothing less than 0. Second part, when x between 0 and 1, okay, then fx will equal to so we only care about 0 to x. Again, because less than 0, it has nothing there. Okay. Fx t to the power of 4 dt. Okay. And I just skip the remaining. Then we should also be complete if x larger or equal to 1, then fx will equal to 1. Again, because the whole areas, when x is larger than 1, we should consider the whole areas under that curve. And we know already with our calculation, the whole areas is 1. Okay, it's 1. Okay, any questions so far? Okay, so the idea is pretty straightforward, but the integration part, we just, one, how to do integration, depending on the equation, and two, be careful about the range, especially for cumulative function, you should discuss different range. Okay, then the equation may change a little bit. Okay. All right. So we discussed about the mean value, the mu x. Okay. The median. Okay. the median function given like this. So fx, m is for median. Okay, so we resolve the equation of this. For px less or equal to xm, which means the areas under the curve will equal to 0.5 or 50%. So which means 50% of the chance it will be smaller, and 50% of chance it will be larger than xm. Okay, all right. All the areas underneath the curve will be 0.5. For comparison, the mean value mu x is this. Dx. Okay, so the mean value is x times fx dx. But for median, that's resolved by this equation. Okay, when the probability is equal to 50% fx dx. And percentile, based on same idea, we can calculate for any p-value, any percentile. So the p percentile is the point for xp that resolve this equation. Okay, so based on this equation, whatever the p-value is, you can resolve the p percentile fx dx. And of course, the median is the 50th percentile. All right. This is the last slide of section 2.4. Okay, this is called Chebyshev inequality. Okay, so that shows us inequality equation for mu x. Mu x is the mean value, and sigma x is the standard deviation. Okay, so this equation inequality is valid for any random variables. Okay, even if we do not know the spread of the, if we do not know the distribution, this equation still holds true. And k is any constant. Right? But if we know the probability density function or the max function, we can actually calculate the actual probability. Okay. But remember, this is always true no matter what the distribution is. Okay. So that's the end for section 2.4. So random variables, we discuss discrete variables and continuous variables. For discrete variables, we have probability mass function, okay, and also cumulative function. For continuous variables, we have probability density function or PDF, and also we have the cumulative function. The calculation is more complicated for continuous variables, of course, because we need to do the integration. But the idea, I think, is not very hard to understand. Okay. All right, so let's continue for section 2.5. So linear function of random variables. If we see x is a random variables and a and b are constant, and then the mean value for ax plus b is equal to a times mu x plus b. Okay. For the variance, so the variance of ax plus b is equal to a squared times the variance of x. Okay. And the standard deviation of ax plus b is equal to the absolute value of a times the standard deviation of x. if we have more than one random variables, okay, x has the y, and a, b are constant, then this equation also holds true. So this is called the mean value of ax plus by is equal to a times the mean value of x plus b times the mean value of y. Okay, so more than two variables, so this equation also holds true. So if we know x and y are independent, okay, random variables, and s and t are set of numbers, okay, and this is the probability the value of independent variable x is in set S. So this is x in set S. So S and T are set of number, and y in the set of T will equal to the probability of x in set S times the probability of y in set T. Okay, so providing x and y are independent. Okay, all right. So here is something wrong with word. So more generally, if you have more than two independent variables, okay, and then this is sorry about that. This is x1 within S1, and this is x2 in set 2, and so on, which is equal to px1 in set 1 times ps2 in set 2, and so on. For variance, if x and xn are independent variables, okay, then the variance of the sum, again, so this is x1 plus x2 plus dot 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 plus xn, okay, is given by variance of x1 plus variance of x2 plus variance of xn. Okay, and if x1 to xn are independent variables, okay, and c a constant, then c1x1 plus c2x2 dot 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 plus cnxn is given by this equation. Okay, so just pay attention. The constant become the power of 2. Okay. And for two independent variables, x and y, the variance of x plus y is equal to variance of x plus variance of y. Pay attention here. The variance of difference between x minus y, okay, is equal to variance of x plus, this is no typo, this is plus variance of y. Okay, so that part is important. Another example here. So piston is placed inside the cylinder. Okay. And clearance. So let's draw something here. Okay. The clearance is distance between the edge of the piston and the wall of the cylinder, and is equal to 1/2 the difference between the cylinder diameter and the piston diameter. Okay, let's say this is the smaller diameter is diameter of the piston, dp, okay. And the larger diameter here is the diameter of cylinder. Okay. This piston. Okay. And let's define the diameter of the cylinder as x1 and diameter of the piston as x2. Okay. So the question tells us the clearance is the distance between the edge of piston and the wall of cylinder and is equal to 1/2 the difference between cylinder diameter and the piston diameter. Okay, so let's see. C is for clearance. C is equal to, it's at 1/2 of x1 minus 1/2 of x2. Okay, so that is clearance. Clearance, C. All right, so this is what the question tells us. The question also tells us the piston diameter has a mean value and standard deviation of that. So piston diameter here, which is x2. For the cylinder diameter, which is x1, the mean value and standard deviation. Okay. Question also tells us these two diameters are independent, asking for standard deviation sigma of clearance. So sigma c. So ask for this. Sigma c equal to what? All right. So we know c is equal to this equation. Okay. So sigma c is equal to sigma 0.5 x1 minus 0.5 x2. Okay. So based on the equation, the constant is 0.5. So that is equal to 0.5 mu x1 minus 0.5 mu x2. Okay. So mu x1 is given. Okay. And so does mu x2. So the mean value of the clearance mu c is equal to 0.05. Okay, then let's look at the standard deviation. Okay, the standard deviation again is sigma c. C is for clearance. So that is square root of the variance, because c is equal to 0.5 x1 minus 0.5 x2. Okay. Which is equal to 0.5 square sigma x1 square plus is minus 0.5 square sigma x2 square. Okay, so this is based on this equation. Okay. And then we can plug in a number. Sigma x1 is equal to 2.02. Okay. And sigma x2 is equal to 2.03. Okay. So the standard deviation of the clearance, sigma c, is equal to 0.018. Okay. All right. So questions about this example?
Well, what does mu represent in this?
Mu is the mean value. Mean, the mean value. Because the question is asking for the mean clearance, which is mu c. Okay, so the mu c is equal to 0.05. And standard deviation is called sigma. Okay, so you will become more familiar with this. Mu is the mean value. Sigma, standard deviation. Okay, variance is sigma square. For samples, variance is S square. Okay. Okay. So independence and simple random samples. If x1, xn are simple random samples, then we may treat x1 to xn as independent random variables. Okay, and always the same type of distribution. Okay, when that's the case, they are also called independent and identically distributed. Okay, if they have the same type of distribution. All right. So we have 2 more slides for today. Let's talk about the sample mean, the property of sample mean. Okay. If x1, x2, xn are simple random sample from a population with a mean value of mu and the variance of sigma, okay, then the sample mean is always like this: x with a line on top. Mu sample mean, which is the mean value of the sample mean, that is equal to population mean, mu. Okay. But the variance of the sample mean is reduced, is smaller than the population variance, sigma squared. Okay. So the larger the sample size, the smaller the variance of the sample mean. And the standard deviation is this. Okay. So that tells us when we have n simple random samples, when we increase the sample size n, then the mean value of the sample mean, again, this is mean of sample mean. Okay. What is sample mean? Sample mean is this. Okay. So the mean value of the sample mean does not change. However, the variance becomes smaller when we increase the sample size n, as we can see from here. Increase the sample size n, the variance and the standard deviation goes down. Okay, so what does that mean? Look at this, the last question for today. Okay, So a process fill plastic bottles with a beverage has a mean fill volume is and the standard deviation of that. Okay. And that case has 24 bottles. Okay. And assume the bottle in the case are simple random samples and find the mean value and the standard deviation of the average volume. Okay. So we have 24 bottles. So let's define V1 as for the first bottle, the volume. So V2 is volume for the second bottle, and so on. We have 24 of them. Okay. So the average volume V average, so is equal to V1 plus V2 plus V24, and that is divided by 24, right? So that's average volume, 24. Okay. So based on this equation, the mean value of sample mean does not change. Okay. So the mean value of V average, this is mean value of volume, average volume, is equal to the population mean, which is giving us 2.013 liter. Okay. But the standard deviation does change. Okay. The standard deviation of volume, average volume, okay, is equal to the population standard deviation over square root of n. Okay. So the population standard deviation is
I didn't get that. Could you try again?
is 0.005. Sorry. Okay. The sample size
I
is
didn't get that. Could you try again?
sorry. Square root of 24. Okay. So 0.001.
The square root of 24 is approximately 4 point.
Sorry. I hope you don't hear that. All right. So let's stop here. Okay. So we discussed section 2.4, 2.5. We may have probably 1 or 2 lectures remaining for chapter 2. And after chapter 2, we're gonna do the practice sessions all together. So we're gonna get questions from chapter 1 and 2. We resolve these questions together before we have the first homework. Okay.